Signal analysis in economic engineering. Signal analysis is a pretty abstract, one of the more abstract things that you're learning here. And at the same time, the abstraction is a strength, and because that means you can apply it to everything. And at the same time, when it's abstract, it is just abstract and it's harder to understand. So what I want to achieve with this lecture is to show you the strength of the abstractness by doing two things. First, I'm going to apply signal analysis to a topic, economics and finance, in which you've never seen it applied. Right? Our normal applications, in this course, the applications you get are all to mechanisms, spring mass damper systems, or to electronic circuits. But you won't see very much applications to finance, maybe a bank account, but it's a very limited kind of example, okay? So what I want to show you is a big model that we analyze using signal analysis. The other thing I want to achieve is to get rid of the abstraction parts, especially of the Fourier transform and the Laplace transform, and show you that in its economic interpretation, this thing is very easy to understand. All the formulas become obvious. The use of complex numbers becomes obvious. And a lot of things become very intuitive and obvious. And that's just a way to work with this stuff. Because if you have that in your mind as the intuition behind the abstract concepts, it just makes you so much of a better engineer. And then the other thing I want to show to you that it's just a lot of fun being a control engineer in systems and control, because you can just do anything. All right. And that's also the reason why I am in this topic. So at DCSC, we have a group. It's called the Economic Engineering Group. And what we do is we apply the concepts like signal analysis and controls and systems modeling and dynamical systems, not to engineering systems, but to economic systems. And in this sense, we call it indeed economic engineering. So it's really engineering but it's economic engineering, just like mechanical engineering is engineering, but then for mechanisms, okay? And this is my name, Max Mendel, and I have a bit of a checkered career. I started at this place a long time ago when it was still called the TH, for Technische Hogeschool. And then I did a PhD in the States at MIT. I became a young professor at UC Berkeley. And then I quit academe, and I was active. This WS means Wall Street. And I started trading, and thinking that all the techniques I'd learned here were applicable there. Well, nothing could be further from the truth. I just had to learn all from the start and the get-go how to do this. And then after that period, I did nothing because I didn't have a real job or anything. And during that moment, I started thinking about how to tie these two aspects together. So how to use all these techniques you learn in engineering school, how to apply these to finance. And that's how I came back to the same university that's now called the TU. And we're have a group where we're doing this. Okay. Now, so signals in economics. Now, the first thing you'll realize when you start attacking this problem is that they don't have the concept of a signal. They don't have the word, but you would think they may still have the concept, but even that is not. Because if you think of what a signal is, it's an entire function. Usually we think of it as a function of time. So it's not just time, and it's just not the value, but it's the whole function. You take the whole function, a whole sinusoid. Here it is, all right? Or you take an exponential decay. Here it is. Or you take the superposition of this. That's a damped sinusoid. And here it is. This is the signal I'm putting in. And then you put it in a box. Okay, that's the system. And that has a transfer function or something, an operator. And it changes the signal and it pushes it out again. And then, there you get another signal out. So what's special about signal analysis and systems thinking is that we're not dealing with numbers, but we're dealing with entire functions that we're moving around and we're analyzing, okay? Now, this is not the situation in economics. So in fact, it's very different. So here I have two models. This one is the so-called circular flow model of economics. And it's taken from a very popular macroeconomics book. I think it's Mankiw. I know it's Mankiw's book. And then you see these blocks, markets for factor of production, financial markets, government, goods and services markets. So they have these markets and then they have household. They look like systems and these things look like signals, but they really are not. In fact, this is just a number. So this is what they call the circular flow model, and there are just payments flowing, and that is always a constant, so they'll just say this is a number, all right? And this is a number too. Now they may change things over time, and they'll have a time series, but then they'll just have the number change a bit over time, and they adjust to a new equilibrium state. But it's not something that's happening either in continuous time or discrete time, where it has a repetitive value, all right? So it's very, very different in terms of its thinking. It just looks the same. Here's another number. It's called a dynamic stochastic general equilibrium model. Again, the E for equilibrium means the whole thing is in equilibrium, all right? And there's no way to get it out of equilibrium except going immediately to another equilibrium state. The word dynamic, nobody's quite sure why it's in there. If you look up the critiques of this type of modeling, even economists will say there's nothing dynamic about it. I'm not quite sure what the dynamic does. This is from the Federal Reserve. They use that to, purportedly they use this to set interest rates. So in order to talk about systems, signals in economics, we first have to kind of start doing the work. All right, to really get a signal, and then we can analyze that. Now, suppose you do that as an engineer, then you first need a system, and because you want to use the Fourier transform and the Laplace transform, you'll probably want a linear system because sinusoids they're the eigenfunctions of the of linear systems. So the Fourier analysis makes some sense. So you'll do a whole bunch of things. So here I have another slide. I'm not going to talk too much about it. You'll drop some mechanism. So this is a typical mass spring damper system. You've seen this in the course. Here's a circuit. You know that these things are equivalent, right? So when you model this, they both follow second order differential equations. And there's a sort of analog between the mass is the same as an inductor. And why is that? Well, the mass is something that maintains a velocity, so you keep it going, and you need a force to change it. And an inductor is something that maintains a current through here. So the current just keeps flowing, and then you need an EMF, an electromotive force, and a voltage over this. Here's the inductor. I'm pointing to a resistor. This is the inductor, okay? Sorry about that. So you need a voltage over this to change it, okay? So what we have done, this is called analogs, and what we have done in economic engineering is make an economic analog to this. So what is this velocity, or what's this current? Well, that's a flow of goods, say so many barrels of oil a day. And then what is the inertia? Well, that's the thing that maintains this flow. All right, now what would maintain the flow? Well, demand, of course. If there's demand for oil, then it keeps it. So you'll see that demand is the inertial element, and a spring or a capacitor is just the storage. So you can have a storage of oil, and then it will go in there. And then these frictions, they're just transaction costs and other things, okay? So you can figure out how you can make it economic system with these analogs. You can draw a kind of electrical system or a mechanical system that does the equivalent thing if you just kind of fill in what you do. I don't want to talk too much about this because this lecture is all just about the signals. I just want to say, normally if you're going to look at your signals, you first need a system to see you push it in and push it out. And the only way to make the system is to do the hard work and build this. Now, once you have this in place, you can build something. So here we built something. This is a big system that is comparable to both of these, All right, so you can recognize some of the blocks like households and firms. Here's households, firms, there's some banks, there's the government. And this is just an electronic circuit. We could have taken anything else. All right, and it works a little bit different than the economic systems, and then in the following way. So here you can see all these little things. That's not important. But what's important is we're using this technology here called N-port, multi-port theory. So the only thing that's good about it is that you can draw these boxes around it and then communicate with the box through something they call a port. And on this port, these are electrical engineers. They have a current, so that's a velocity for us. And over this current, so it's like a loop, they have the force, the voltage. So these communications, they come in pairs. So there is a voltage and there's a current. The voltage is the incentive, economically speaking. And the current, that's the flow of the goods, right? So here is money flowing, and there's an incentive that will push this person to add something to his checking accounts, okay? And for all the talk about dynamics, you know you will only get dynamics if you have the notion of a force, okay? The force is the thing that tells you how the motion is going to change. In electrodynamics, it's the same thing. You won't have any dynamics unless you have the notion of a EMF or a voltage that you can apply and then change the currents in this way. All right? So this pairing between a flow of goods and the incentive is the thing that you need to make this truly dynamic. And if you look at these, you see there's no way, these are all flows. There's no force, you know. So you'll never get really dynamics. And if you don't have any dynamics, you don't get any signals because nothing is changing. And then you won't be able to do a signal analysis. Okay? Same thing here. You see goods are flowing, capital, but what's the incentive? What's the desire of people, right? What regulates the behavior in time? This is for another courses. We'll give you some links below where you can look up on how you actually do that. But now what I want to do is make the big leap and show you that we've really got signals now and we got systems. So we'll do a little demo in a little bit, but the idea is that now we can do this kind of signal processing. So here you see, here's aggregate demand. So households are demanding goods and services from these firms. And what we're going to do is you can see now how many goods and services flow through here and what their incentive is to get them. And what we're going to do is we're going to set a shock on that. Okay, so we're going to say, hey, COVID came, so we're going to have some demand shock. That's here. And it's a COVID demand shock. So it's going to be, what did we have? I think we have a step, right? All of a sudden, people are going to stop going to the bar and they stop drinking beer. This actually happened. Okay, so we get a step. There's a real signal on here. And these households are now a real system. So we can go with our probe and then look what happens to aggregate demand. I'm not quite sure what it is. Oh, it's right here. And then come to the firms, and we can then see these firms, they need to borrow money from banks. You know, they get their loans from the bank, and we can see how that affects the amount of loans that are coming out. Okay. We can also see if there's a demand shock, so nobody is buying beer, what happens to the wages? Probably the wages are going to go down, and people are going to get fired, and I don't know what. And that's going to come back to the households, okay? And lastly, we can see there's another shock that will show because the government put in these subsidies and they started giving money to the households. And then we can see what that does. What are they going to do with that money? Are they going to spend it, or are they just going to put it on their savings account and do nothing with it? Now, in hindsight, we know exactly what happened, but in foresight, we did it. This is a project we do with the bank, and the bank had it wrong. So we'll see a little bit how it really worked out. Okay. So we'll give a little demo about that. Now, you know, it's one thing just kind of figuring out what happened, and the other thing is doing something about it. So Now that you know that you're getting your deposit and your loans go out of control for a bank, now if the bank gets a lot of deposits and they have no loans, they're not going to make any money because they pay interest on the deposit and they got to receive interest on the loans. If they're not receiving anything, right, they're just paying, and they're probably not going to do well for them. So they need to adjust the interest rates in order to entice you to put less money in your deposits if they have too many, and entice the firms to start borrowing money. So they got to reduce the interest rates, and they do that in various ways. So there's a department at the bank that does that. It's called the ALM department because they manage the assets and the liabilities. The loans are the assets, and these are the liabilities. And the managing, that can be done by a controller. Yes, a controller. So we'll also show you a little bit how we can look at a target ratio that the bank wants to maintain, how we can implement a simple controller. You get an interest rate incentive out, so you incentivize the right parties to do whatever you can. And then you put out this another financial ratio. The financial ratio are defined by the regulators like the ECB and others, as the risks that they need to keep. So we can do this all using our little control loop. So you can see these are real signals. There's an error signal, and we get real block diagrams with these breakout points and summers and all of that. All right. And then after that, we'll start doing the analysis. But for now, first, to make this all real, let's take the model for a test drive so you get an idea of what's going on here.
So we've got the model open over here that Max previously showed. And what I've done is I've applied the COVID demand shock over here on the left. So this COVID shock is applied to the aggregate demand of households for goods and services. And now we can follow how this shock, this incentive, propagates throughout the entire model and finally affects the loans and deposits for the bank. So we will run this model. And here we are measuring the COVID shock. And we can see that at the COVID shock is a step applied at the 30th time step. And is applied for the entire, till the end of the horizon. So we can measure the aggregate demand. And we can see that as a result of the COVID shock, aggregate demand falls down. So households are not buying their goods and services anymore. And this shock propagates through the model, so to the aggregate supply of firms. So their supply goes down, and in response to their, to the low demand and the low supply, firms will change their investments. And we can measure that over here at the top of the firms. And we can see that their investments go down, meaning that also the loans they issue at the bank will go down as well, which we can see over here. So after the COVID shock is applied, you can see that immediately the loans issued go down. So the amount of cash firms borrow goes down because of this COVID shock. Now we can also follow how the shock affects wages. So this is an interesting result. We see that at first after the shock, wages go down. So firms do not need as much labor as they used to because they are supplying less goods and services. So wages go down. And in response to the decrease of wages and the resulting decrease of income for households, the government intervened with subsidies. And this is also a second thing we can input in the model. So we have the government over here. And now we can measure the amount of subsidies they supply to households. And we can see that, they're a bit lag behind. So 1 month later, for example, they started providing these subsidies after the COVID shock. And now we can measure the income for households as a result. And we can see that first goes down because of the lower wages, but then because of the subsidies, it goes down and maintains at a constant level. So households were receiving these incomes, but they couldn't spend it on their goods and services. So as a result, instead of spending the money, they started to deposit all of their leftover money at the bank. So this is the second thing the bank, well, actually saw as a result of the COVID shock, was that their savings increased by a huge amount. And this is where it starts to become a problem for the bank, because now they are paying all these interest payments for these savings deposits. But meanwhile, the amount of loans they issue went down. So their interest income started to decrease, whereas their interest expenses started to rise. And this is also something we can measure over here at the bank. So this is their net interest income. And you can see that their net interest income starts to decrease after the COVID shock. So their profits starting to, well, to decrease. And now we can apply feedback control in order to, to steer the amount of deposits that flow into the bank and the amount of loans that flow out of the bank. By using the loan to deposit ratio as a target. So we set the target ratio for 120%, which is shown over here. And without any controls, we can see that this target ratio starts to decrease after the COVID shock. So now by lowering the interest rates, instead of keeping them constant, the bank can incentivize the firms to borrow some more money from loans and to decrease the amount of savings they receive from households a bit. So we will turn the interest rate control on and run it again. And now we see that at first we have the same response. So the loan to deposit ratio starts to decrease. However, we can see that, well, very fast the bank is now reacting to this COVID shock and changing the interest rates in order to steer the loan to deposit ratio back to its desired target. We can also measure the interest rates that the bank uses in order to steer this. So we can see that at first the interest rate is around 1.6%. But then after the shock, they start to decrease the interest rate. Well, exactly to adjust the loan to deposit ratio. And as a nice effect of this management by the bank, we can see that instead of the profits, the net interest income of the bank lowering over time, we see that it increases again.
Okay, so what did we just see here? What we saw were what we would call real signals. I remember there's a green signal, I forgot what it was, with a lot of fluctuation in it.
The savings deposit.
Savings deposit. So you can clearly see, if you had paid attention, or if you wind back the video, you'll see two frequencies in there basically. All right. So there is frequency content in there. All we saw now is a bunch of time plots, and it's really great, and you can see what's happening over time. But you can see this whole thing is probably much better analyzed in the frequency domain. It all becomes simple, and we can make graphs like this. Instead of stepping through, we can think of these as Laplace transform or Fourier transforms, and think of these as transfer functions, and a very simple structure that we use in systems and control for controlling and analyzing these will emerge. And that's going to be, now that we have a grip, we have a model, we have an LTI system, we have some fluctuations going on, we can give shocks, we can control. What I now want to do is go on and talk about the frequency domain and show you how we can use those tools to do so. And in the end, we'll do another filtering examples where we do this. All right, so skip over this. And first I'm going to talk about the Fourier transform. Okay, now here I put the Fourier transform. All right, so think of this now as some kind of flow. This is a velocity, so it's a flow of goods or a flow of food, or in this case, maybe grain coming out of this harvest, okay? And it's a flow in time. And then you multiply it by this complex number here, and then you add it up over all of time. Okay, what happened here, right? What happened here? This is what I want to go through. I want to totally decipher this formula. I'm going to start with this formula, which is the discrete time Fourier transform. All right? Now, here we get the same flow of the goods. Now I'm going to go to this picture over here. And then and here it says, this is a picture that's a typical picture they use in agricultural kind of research. And here you see this says harvest here. So I'm going to draw a real axis here. And I'll call this +1. And then I'll put the 0 here, and I'll put a -1 over there. All right? Now suppose that you're just a hunter-gatherer. So this is no farming going on. So you're just running around and every day, and you find a seed or a bag of seeds, I don't know, some berries, right? We're talking about seeds here. So this signal of yours is you're gonna see, if you look at it in time, you're gonna see a 1, right? Huh? And then another 1, and then another 1, and another 1, and another 1, and another 1, right? Huh? And you're gonna have a nice signals of only ones. Boom, 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 boom. No, you know, nothing needed, no complex numbers needed. You just have the signal, and that's it. Okay. Now you get more. You get a little bit more efficient, and you say, well, I'm now not going to be a hunter-gatherer. I'm going to be a farmer about this. Okay. So what does the farmer need to do? The farmer actually needs to plant the seed. So that's -1. In a certain part of the year, and 6 months later, he'll get the seed back. All right, he'll probably get more, but say this is just a subsistence farmer. So now he has another sequence. First he gets a 1, he's got a seed, then he gets a -1, so then he gets a 1. Huh? I guess this is a good discrete time signal. You know, and he's doing okay. He's still just using real numbers. And he's got a nice alternating series, and just the way you learn it, you can do that, right? Huh? So you have a nice little signal, first a 1, and then a -1, and then a 1, and then a -1. But that's not what actually happens, because you can't just put a seed in the ground and then walk away and expect everything to work out, because somebody's going to eat the seed or take it out, or it won't grow, you know. So there's a couple of things you need to do if you're a farmer. And here they tell you what it is you need to do. There's going to be a protect, and I'll put another 1 here, but I already ran out of real numbers, so I'll use some kind of other real number. I'm not going to call it imaginary, because there's nothing imaginary about it. I'm going to call this the number I. It's like a Roman 1. Small, lowercase Roman. And then here I'll put the -I. All right? So now what's happening? Okay? What's happening is that I now go through first a seed, then I have to go and protect my land, you know? So I gotta put all this manure. I don't know exactly what they do. Then I plant the seed. Then I'm -1. And then I have to prepare for the harvest. So I do all kinds of other stuff. All right. And then, only then, do I get this seed. All right. So now I have a signal that consists out of a 1, an I, a -1, a -I, and a 1. All right. Now, what's so cool about this? Okay, you say you just did something arbitrary. But the thing is that it's not arbitrary. This is the only way to get it fixed, okay, using the imaginary I squaring to -1. And to see that, you see this as follows. So if you look at these formulas, you see they do kind of do 2 things. They add, right, and they multiply here. Now, things that add and multiply, we call that an algebra. So you need an algebra. It has to be able to multiply and to add. Now, adding is easy. You have 2 seeds. Okay. All right. I got 2 seeds out, so I just added another seed, and I got put 2 seeds in, and I get 2 seeds out. That's the easy part. Okay. Huh? The multiplying is a little bit harder, because we're going to have to multiply complex numbers. Okay. So what the multiplying actually does is it tells you how you evolve. Huh? Okay. Well, evolve comes from volvare, which is to roll, right? An evolution. Huh? Okay, a revolution, you just kind of re-roll the thing. Huh? So you can think of this circle as the way the time rolls for the farmer seasonally. all right? So the evolving, that gets done by multiplying. So if I'm here at 1, then I want to start, when I want to go to the protect phase, I multiply by I. So this is 1 times I. Then if I want to go and plant seeds, I have to multiply by I again because I'm advancing a quarter. So this is quarter 1, this is quarter 2. I'm just a little weird quarter counting, but it doesn't matter. So every time I advance a quarter, I multiply by I. So you'll see if I multiply by I, and again, I'll get I squared, I gotta come up to -1, all right? So this has to be I squared. So you see you're stuck. You've got to use complex numbers. Otherwise, your algebra doesn't work out. You have to invent a whole new algebra, all right? Huh? So the business of farming, at least the quarterly business of farming, requires 2 types of numbers, real numbers and complex numbers, all right? Imaginary numbers, sorry. Now you say to yourself, well, I work in quarters. Like here's a farmer, and he works in months. So he's doing his harvesting, just like the other guys are. But here he is giving somebody the jab. Here he's playing around with his tractor. So he's divided it up in all these subtasks, okay? Now this can be, this one is I and this is minus I. So what do you get in between? Well, you'll get some other number in between. It's a complex number. It's a little bit of the real stuff and a little bit of the preparation protection stuff. And that is exactly this number, which is the fundamental frequency here. And you take e to the power of it, all right? So you get some complex number that give you the months. And as you multiply these together, you take this to the nth power or kth power here, you'll see that you step through your 12 months. So here the fundamental frequency is, 12, huh? Okay. So this is how you end up with complex numbers. Now you have no choice. You have no choice. So now you're getting very close to these type of signals. Okay, so these are complex signals. Now you can say, well, why stop at a month? I don't go to days, and I don't know what. You can go in the limits. I count everything. And people do that, okay? So when you do that, you can, for instance, with money, you do it this way. So you see, money didn't exist before this existed. First you have farming, and then these farmers make a surplus, and then you need money, and that money, the farmer has to then borrow money in order to buy the seeds and the equipment to put this in, etc. And so they invent this credit system. So you get the cash, and then there is the credit, all right? And it goes through the same kind of cycle. So before you have a receipt of cash or you make a payment, there is another phase in between. So an accountant will book this as an accrual. It's called in Dutch a voorboeking. And this is a cash payment. Huh? And this is then an accrual payment. And you first accrue it, and then you make the payments. All right? So first this is more of the legal thing, and this is the transfer of the goods. So this is the agreement. So first you make the agreement to transfer the money, and then the actual transfer, that's called the settlement sometimes, okay? So this goes in a cycle too. This one's called the credit cycle. This is called the crop cycle. They got tons of cycles, okay? And you can think of an entire economy as consisting of all these cycles. So I can take one cycle. Here, this is a farming cycle. On top of it, I put a little faster credit cycle. You can borrow money every month here. All right. So, and then I can put them together, and I can get the signal of what's going on. Okay. So then I get this signal. Okay. And this is actually the property of the Fourier transform. So you can put another one on there and another one on there. And this is how you build one of these things, right? So you add them all up. Huh? So basically what you're doing is looking at the different cycles that are there in your economy. If you only have one cycle, this one, you're going to have a simple spectrum of just one impulse, Huh? It probably only goes one way. It could go the other way. That's when you're short, okay. Huh? Okay, so and then this is the continuous time version. So where do we stand here? Well, one thing that's interesting is just sort of a philosophical thing, is that something that's called an imaginary number is not that imaginary, right? It's just something that is as real as anything. There's sometimes taken the attitude that when you do these Fourier transforms, that you just throw away the imaginary part. And if you're only interested in seeds, that is nice. But there's really no point. You can imagine there is something that's going on, okay? The way Gauss looked at it, he also didn't think it was imaginary. He had this idea of orienting yourself. So he used the imaginary numbers for rotations, 90-degree rotations. Here we see the rotation, there's a quarter passing by. It's all kind of related, all right? So this whole business of the Fourier transform and the cycles, they call it seasonality in economics. They're really, I'd say it just starts with farming, which is 12. That's when economics starts to, you know, first when you settle down, you have farming and you have a surplus, and then you have economics, and you get a credit cycle, you get all kinds of cycles, you know, and then you have an economy, and the economy is just based on cyclical movement. So if you looked at the model we saw that green line all wiggling about. These are just various cycles that you'll find in your economy. If you look up the business cycle, you'll see there's like 7 of them that they've identified, inventory cycles, this and that. So implicitly, there's this idea that, economics is also somehow described by an LTI system, because otherwise, how can it sustain these cycles? You know, there has to be some kind of natural frequency. Economists, they may think it's all force, but that's not really possible if you take the system lines to be the whole economy. All right? So much for the Fourier transform. I now want to move on to the Laplace transform. And what I want to do here is only look at the real part of the Laplace transform. So this S here, this is the Laplace transform I put here. This is the Z transform. It's just this periodic brother. And normally you look at this S to consist of a real part sigma plus this imaginary part I omega. Now this was the Fourier transform, so we did that before. So let's leave that alone. We can put it together later. I'll just focus on this real number here. All right. Now this expression here, you get to learn this. You can stare at this for as long as you want. But as a student, you quickly figure out that doesn't change anything in real life, because whenever they use these Laplace transforms, they don't really care what this expression is. You just have to go to your lookup table and you look up the right thing and you just plug it in. All right, so this just seems a little bit strange. And I have to agree, it is. And it's maybe worthwhile to say how this grew, because the Laplace transform has a bunch of properties, and one of the properties is that differentiation in the time domain, I got it here, I'm going to talk about what this means economically, is multiplication in the frequency domain. Now, if you know that, then as engineers, you don't like to solve differential equation. You much prefer algebraic equation. So if you have some tool where this turns any differential equation, linear differential equation, into an algebraic equation, that is great. You look at the poles and you start doing all kinds of fun things, okay? It's a guy called Heaviside who did that, but he was ridiculed by the scientific community because it had no rigorous basis. And then somebody figured out that this Laplace transform is actually the tool you can use to do that, this formula. And then everybody had a sigh of relief, and they say, all right, if we just say we go to the Laplace domain, we can just carry on as usual and do our trick without feeling bad about ourselves, all right? So that's a typical thing engineers would do, and you don't want to feel bad about yourself. You want to think you're rigorous as anybody, but you don't want to be bothered doing it, and for good reasons, because otherwise you get nothing done. Now, what I want to do here is totally decipher this so you won't forget it. It's completely intuitive, and that the rest of the stuff is intuitive as well. All right? That's what I'm going to do. So now forget about what you knew about the Laplace transform, and just think of this as some kind of flow. And I'm going to focus on money, but you don't have to. It can be anything. All right? Now, so this thing, V of t, is some flow of money. So I use a time, and then here is time 0. And suppose I give you €1 at time 0. Here, boink. There it is, boink. You can ask yourself how much that's worth. Well, that's a stupid question because €1 now is worth €1, right? Okay. Then I say, well, I'll give you that, but I'll also give you €1 1 year from now. Now, how much are these two payments worth together? Now, this one was €1. This one is a little harder, right? I mean, that can't be worth €1 because it only comes a year from now. Maybe this is 100 years, then it's worth absolutely nothing to you because you won't even live that long, right? Huh? So a year you can still imagine, but you're certainly not going to think this is, huh? So you're going to say, well, maybe it's worth 50 cents or something. I don't know. I'm just making something up, but something less, right? So you're going to multiply this payment by a half, right? And then you have 50 cents here. You have €1 there, and the whole thing is worth €1.50. All right, and that's what you should be willing to pay now, to get this money flow. Right, that's the thinking, and this is called this factor that brings it down, squashes it, as Gabriel says. This is what we call discounting. So you discount it, and that factor is called the discount factor. And you can do this for any time t. So you'll see the z here is this discount factor. This is actually, you do -1, so it's actually the future factor, the forward factor. That's how much you would have to pay extra, all right? Now you can do this in continuous time, and you'll have something like this. And then you'll have to do this integral. And then this is this discount factor. So for any time starting from 0 all the way to infinity, potentially, right? What you do is you take the payment and you multiply it by the discount factor, and then you move on. All right, that's all this thing says. It's something that's very easily understood, right? Huh? And this thing, this value you get out, is what the economists will call, or a financial type, an accountant will call the present value. Present value. All right? I think I put it here somewhere. So this is the present value. Okay? Now what economists do not do is to think of this as a signal. They think of present value just as a number. So they plug in some kind of discount rate S here. They get a number out and they say that's the present value. Now the twist you got to make is to say, I'm going to not plug anything in. I'm going to leave this S unknown. So I'm integrating out over t. So I'm going to get a function here of the discount rate. Okay? And obviously the total value will change if the discount rate changes. Okay? So if the discount rate is 0, that means I'm not discounting anything and I get 3 payments. These are now impulses. This is just going to be 3. But if the discount rate is infinitely big, the first payment will get through and these ones will get canceled, and now it's only 1. And it's going to be somewhere in between. All right? Okay? So the Laplace transform you can think of as the process of discounting. All right? So you can take any signal, and then even if it's like growing, you can discount it appropriately, and then later you may want to do a Fourier transform or whatever you want to do. But you can see this as the process of discounting, and the value of the Laplace transform, that is the present, what is called the present value. All right? Okay? That's the thing you have to keep in your head. And you've got to see that this present value is a function of the discount rate. And then you're in business. All right? I want to show you how you're in business. Now you can do this all with the Z transform too. I'm just going to keep it simple and just talk about this Laplace transform. All right? Now, the other thing to kind of realize is, what are the units here? These are euros per year, because that's how much money you get, right? And these things are in euros, right? So the present value doesn't have the same unit as the time variable, right? It's sometimes forgotten in engineering. Why not? Because you multiply by t, right? So if you get a flow here, you got some kind of stuff, a stock over there, all right? Just keep that in mind for the interpretation. Now let's have some fun with this, okay? So here it shines. So I have a table. This is the typical table. I took a little piece out of it, and I want to show you just how easy it is to think this way. So this is a delta function. Now, what's a delta function? Well, here it looks, right? Here's time, here's 0. Well, we all know what that is economically. That is getting a euro now. So this is 1 euro now at this moment, and 0 euros everywhere else. In the past, in the future, I don't care, right? The past is not so important for this integral. How much is that worth, right? Well, 1 euro. Already said that. Here it is. How does that depend on the interest rate? Well, it doesn't, right? Because the discount rate will only affect the things that are deferred, that come later than now and then on. So it's not gonna do anything, right? Huh? So the thing is independent of the discount rate. So if I here plot the discount rate, and then I have to plot this value, it's just this, okay? Now it's an interesting result, right? Because the more localized you know, this is super localized. This payment, you have no idea what the discount rate is. And of course not. If this is what's sometimes called a spot payment. Huh? So, but spot delivery, you have no idea how people are discounting in the time, how much time is worth. No, because nothing is happening in the future. All right? Huh? That's all this is saying. Okay, now this is an important theorem because that's usually called what is it called? Duality, Pont-Viagen duality. There's some kind of duality. I always forget. There's some Russian, right? Huh? And the more localized the function is in the time domain, the more spread out it is in the frequency domain, and inversely, right? So here you see the extreme version of that, and kind of obvious, right? Let's look at the second one. It's the unit step. All right, so here's the unit step. So at 0, you get this constant stream of payments. It's like a salary that doesn't rise or doesn't go down, for instance, okay? Or some payment, so continuous payment from your parents or something to every week you get this payment. It's forever. You can also think of it as a certain bond. And bonds are these pieces of paper, and they pay you interest. So you loan somebody money, and they pay you interest. And they have a bond that's called a perpetuity. So it never expires. So you never get your money back, but you'll have interest forever. All right? So what you actually have is a contract that is a unit step, right? It's just eternal. You can pass it on to your children, and they just have this payment. Now, how much is that worth? Well, every accountant that's worth its salt, they learn how to calculate that the value of this is 1 divided by the discount rate, okay? Now, you know that this is the unit step. So how does this thing look? I think here's S, and then this will be 1 divided by S, right? Something like this, huh? Okay. So you see, this is already a lot. This one is half localized, and this one was also kind of half localized. Huh? All right, so this one goes to 0 when S goes to infinity. So if the discount rate is infinitely big, you don't care about any of these future payments, right? In fact, everything is in the future here because you don't have a spot payment. There's no impulse here. So the whole thing becomes 0. It's worthless to you. Okay, there you go. Indeed, if you only live for today, why would you care about receiving interest, right? Huh? You don't. This thing is just worth 0. Okay? So this thing is asymptotes here to 0. Okay? Now suppose you think everything, you just live for the infinitely long and everything is great what happens in the future. So then you put 0 here and the thing will blow up in your face, all right? Now, what does that mean economically? That means that you get a continuous straight payment stream forever and you add up how much money you get. It's going to be infinite. Of course it's infinite, right? But at the same time, you see that this apparatus breaks down, so this whole thing is not converging anymore. That's what it means to be worth infinity. So you know that can't exist because nobody is going to pay infinite amount of money. Right? It doesn't exist, So you're outside of the ROC, the region of convergence. So the region of convergence are those discount rates for which the securities have a true value. They're not valued ridiculously, so they'll blow up the market or something, which cannot happen. Right? The market doesn't let itself blow up. That's way too clever. At least the market is not going to make you infinitely rich, and you'll be infinitely rich if you thought like that. Yeah, because it's worth a lot for you. Huh? The stupid thing that somebody else will sell you. So the market is not going to, all right. So there you go. You can make there's another thing called arithmetic growth. So you get, accountants, these actuaries, they're called. It's a profession, and they calculate these things. And they say, well, suppose my money stream is growing like this. And you can calculate, of course, that this is the value. All right? So this is an interesting one. This is when it grows exponentially. This is called the Gordon growth model. There are certain stocks. And so when you have a stock, you own a stock as shares in some company. You have these models, and what you really own are the earnings, right? They could be paid in dividends or they could be left in, but you're the owner of the company, so the earnings come to you. That's the idea. Now, some of these companies, they grow exponentially. So especially these in the internet boom with Google growing up, you have these companies and these AI companies now like NVIDIA. The whole idea is that it grows exponentially, right? So it may not have much of a profit now, or like sometimes even negative, but it's going to grow exponentially. And the question is, how much is that worth? Well, here you go. This is what it's worth, right? So you can easily look that up in your lookup table, and you'll see what happens. This is called the Gordon growth model. A guy wrote a big book about it. So this is the growth rate. So of course that doesn't converge. So you've got to have a discount rate that's bigger than A in order to get a finite value out of it. And it's still going to be pretty big, So even this tells you also why, when interest rates went down, why these companies got, value is so high. Because if this thing is low and this thing is okay, then it's going to blow up, Huh? Okay. If this is A, you're discounting at the same as the growth rate, then this thing is worth infinitely much to you. Now that can't happen. So you've got to do something. But see this how you can manipulate interest rates. You can manipulate these valuations. This is a very nice way of reading this table. All right. You can go down the list. I just got tired of doing so. And but the message should be that all of this is these things that are hard theorems and the things to understand, and this table that is very non-intuitive, you just kind of remember. You can just think it through, and you can actually do finance with it and trading and all kinds of stuff. All right? I want to move on. So the other great thing is that of the Laplace transform is that as a linear transform, right? So if you have two cash flows, then the present value is just going to be the sum of those cash flows, right? Okay, that's when the A and B are one. That's obvious. You need that. Otherwise, the present value is a silly kind of thing, right? So if you have two bonds, it's going to be worth sum of the values of the individual bonds, right? Now, sometimes you can multiply by positive and negative numbers. So we already had a perpetuity, it goes forever, but our real bond terminates here, okay? And that's called the expiration or the maturity of the bond. So you don't have this. But using this theorem, you can make it from perpetuities, like unit steps. So you take the present value of a whole perpetuity and you subtract from it a deferred one, right? And then you'll get the value of that bond. Now, usually you get some of your money back or your principal back, so you'll have another impulse and you have to defer it. We'll talk about deferral a little bit later, all right? So that's the use of this. And that's how they do it, okay? Now, this is the biggie. This is what I really want to talk about, this imputation thing here, all right? So this is the one that we use it for. This is the derivative is, can be, in the time domain, becomes multiplication by s, all right? Now, why is this is magic, and you can work through it, and it looks like a nice property of the exponential function that if you take its derivative, you get the same function, but then the factor of the exponent comes down, all right? But that's not how I want to look at it. I want to look at it with a very specific example. And the example I have in mind, and maybe you guys don't pay much tax, but here in Holland, there's a good example. What we have is a tax system. We have these boxes. So box 1 is about your income, so it's all in the time domain. When you make income at a certain point, they can tax you. They can take a percentage, right? But if it's in another year, they have to pay in that other year, right? So the timing is very important. Box 2 is the same thing. It's just income from dividends from a company. Huh? And then box 3 is a little bit different. So they try to tax, and I guess I use the word try in the right way here, but try to tax your assets, your capital, right? Your capital assets. So if you have investments, but you're not buying or selling them, nothing is happening in the time domain, okay? Because there's no profit made, right? So how do you tax this stuff? So what the government does is they impute a value. Huh? We also call it forfaitair rendement in Dutch. So they'll say, all right, we're going to assess the value of these assets. So maybe it's a house that's worth this, all right? It's worth $1 million. Here's your house. Any house is worth $1 million apparently here in Delft, right? And then we'll assess this value of this house at a particular rate. So we're going to say the benefits to you from renting it out or whatever you do with it, we don't really care. But the benefits to you are going to be a certain percentage of that, right? Huh? So we impute income, say 5%. I think it's 6% now in the Netherlands. So you get 6% of this, they will assume you make, okay? And they'll tax that at I think the 30% rate or something. I'm not quite sure how the details are, all right? So this is in the frequency domain, right? So nobody's talking about any timing. Nothing has happened in time. But everybody's talking about this thing as a function of the discount rate. So they'll assume a discount rate, okay? And then that's the prevailing interest rates on these assets. And then they'll multiply by, then they'll value your assets and then multiply with it and say, okay, you owe us that much tax, all right? This is what they do. And this is the imputation operator. Okay, so this imputing, so you can see the differentiation in the time domain becomes this kind of multiplication by S, where S is the discount rate. Very easy to understand. This is what you've got to see. And it gets used. Now, the way the government here goes wrong is that they'll do box 1 and 2 in the time domain, box 3 in the frequency domain, and they'll add them up together. But you can't do that. You can't add a time domain and a frequency. Don't you ever do that on your exam because it's wrong. Right? One is a function of time, the other function is a function of frequency, and the two don't match, you know? They don't even have the same units, okay? All right? This is a flow, and the other one is a stock, right? So don't do that, right? Okay? Well, if you multiply by S, then you can, of course, add them. The units are the same, all right? So I guess I spoke. Okay? The next thing is the inverse. That's sometimes called capitalization. I don't want to talk too much about it. This guy I want to talk a little bit about, okay? So this is the inverse of that, right? So here you take a derivative in the time domain and you do multiplication in the frequency domain, but the reciprocal of that is to do differentiation in the frequency domain and multiply in the time domain. Now, what does that mean? Well, let's just think it through. What does this mean? So I have something that has a certain value, right? Say a bond, right? And now, so the bond, and it pays 4%, and I bought it, when the discount rate was 4%, pays 4%, so I'm fine. All right, so I'm fighting inflation. I'm supposedly cool. But now suppose the discount rate changes, right? That can happen. It goes to 5%. Then who wants my bond that's paying 4%? Nobody, because I can get 5% for the same money now. So something has got to happen to the value of that bond, right? It's got to go down. So what happens is you calculate this derivative, all right? So this is called the duration. Why? Because this is as units 1 divided by time, and you divide by it, you get the time there. So it's sort of a duration, okay? The other, okay? Now the duration is what almost all the bond traders look at when they're trading these bonds. So they'll just watch interest rates, see how they change, and they can use this formula to calculate how the value of the bond changes. They have two versions of this duration. This is called what they call modified duration. I'm not sure why. And this thing, which is the time domain equivalent, they call Macaulay duration. Now, what does this mean? Multiplication in time domain. All right. Now let's look through it. It's the same way of measuring this. So suppose you have a bond and you don't get any coupons, you get no interest, but after 10 years, they'll give you 10 euros. All right. These are called zeros or zero coupon bonds or bullet bonds or something like that. All right. Now, what's the interest rate risk on this? Well, obviously, if this 10 was over here, was 0, there will be no risk. And the further this thing is out, the more risk you have. So what Macaulay did, he multiplied this by t. It's sort of the leverage in time that you have, okay? This thing is the maturity, right? So this is when you get it back. Now, if he has got interest payments, he will multiply that also by the time when the interest payments come. So the further out pushed in time they are, all right, the more risky they are thought to be, all right? So that is, for us, same thing. It's just the same trick, but then in the time domain, all right? You can take the second derivative. Some bond traders use that. It's called the convexity. Of course, that's important because if interest rate changes a lot, this thing is not a good approximation. You're going to have to use this to see how convex it is, right? They call that convexity. And then it will be the same as multiplied by t squared. I haven't seen anybody realize this, okay? Right. Okay, so this is some stuff that is useful in when you trade fixed income securities. All right. Let's look at one more. We already saw it. That's a time shift, right? So you shift it in time, subtract some time A, and then in a frequency domain, you get that you multiply by this factor. Now, why is that obvious? Well, I mean, almost too obvious, right? Let's look first at the unit impulse, right? Here it's 0, and now I shift it out, A. I get it here. Well, then I just have to discount it, right? Okay, let's look at a unit step. And then instead I'll shift it out here. Well, what do? Well, I just have to take every point and push it forward. So I just have to discount the whole thing. All right? Huh? So that's all you do. You take any function, move it forward. You just have to discount. Everything is pushed forward. So everything has to be discounted with this factor A as more. Huh? Okay? Convolution is compounding. We saw a little bit of that already. A simple compounding here. This is sort of a compounding, a multiplication by two things. But it's just a general concept of compounding. I don't want to get too much into that. You can go on and on and on with this. But I wanted just to lift out this one and these ones as a really interesting. They always are a little bit magic, and you can see that in finance, economics, it becomes very intuitive. All right. And then, of course, you can put this all together, you can make this a complex number. So, well, what's going to happen? Well, you're doing your production, you're doing your money, you're going through your credit cycle. But maybe this is not going in a circle, but you're like going like this, or you're growing, in which case you'll have a real component that just measures this, the size of your cycle. So you may be shrinking or you may be expanding, so you can put them together, right? Yeah? So the last thing I want to do is show you an application of this, and I'll let you all continue with your own application. So the first application we saw from Behrendt was all in the time domain. We've now developed a nice frequency domain application, so I wanted to step through that. All right. So what I'm going to do is you got this whole lecture on filtering, and I want to show you how you can do supply chain management using the concept of filtering. Okay? So here I have a system. This is an electrical circuit, but I'll describe to you what this is going. So this is a producer here. It's producing some goods. And the flow of goods is this VS, V supplier. The S is for the supplier. Producer. Then there's this thing that's labeled the supplier. It's really where he stores the stuff before selling it. So he has a little storage here, that's that capacitor, and he's paying some money, transaction costs to do the storage, so has the building, has to pay some people to run around, and he's got to, heat the building, I don't know what, insurance, okay? So you'll see the capacitor for the storage, and then this resistor here for the transaction costs and other things. Then there's an intermediary, that may be a wholesaler, right? So this intermediary is giving a price. This is the price the intermediary is willing to pay for it. He has his own storage, and he's making his own expenses. He's taking his cut, which he is spending on an ice cream cone or whatever he wants to do. And then he moves that on, the goods, to the customer, and that's where the demand is. And the customer has no storage. He just immediately eats it. That's the assumption here. So he is willing to pay a certain price, which is exactly the magnetic flux linked into this inductor. Okay, that's the setup. Now, how does this thing work? So these producers, they typically, and these consumers, they typically go in a seasonal factor, a seasonal cycle. So they go at some frequency, they'll put it out, okay? So they go batch, and batch, and they can choose themselves what the frequency is. So these things are pushed through this in a certain frequency. You can also think of the customers demanding at a certain frequency. I don't think this is how it was programmed, but it doesn't matter. This is like a supply-driven kind of thing, I suppose. And then we can look at the response of this thing on the various circumstances. So you can look at this as a filter, and what it does, it takes this frequency and it just finds out what happens at the customer there. All right? So here I have 3 different situations. So the green one is I cut everybody out. The supplier, the intermediate, all the middlemen are cut out. So these goods are being delivered directly to the customer. All right? So the customer feels every frequency. Okay? And he's got to eat the moment the good comes. It's very uncomfortable, right? Nobody wants that, right? So you want to have a little bit of a storage, like the grocery store, and then when you're hungry, you want to go eat this thing. You don't want to be force-fed this, right? So the first thing a supplier may do is to add his own storage, and then he sells it to you directly from his storage, maybe through his web thing. And then you'll get this response, this blue response here, okay? So you see, this is already a lot nicer because only the low frequency, the monthly, weekly ones are led through. The lower frequency and the higher ones, no, I'm not hungry yet. But on a weekly basis, maybe you're more comfortable of taking so many apples, okay? Certainly on a monthly basis, you want to be able to adjust your demand, all right? But maybe also on a weekly basis, but for the rest here, you don't want to do that, all right? So now you can put an intermediary in there, and then it becomes even better. So now you'll see this thing is tuned so that at monthly it gets a huge drop off, right? So it's much better filter, okay? So you get rid of all these high frequencies. These high frequencies are trouble. There are companies like the Toyota Motor Company, and they do this business of just-in-time delivery. So there you really get your stuff, this and this, but it's very fragile, you know? So most companies, they are not capable of. Toyota is an exception on this, and it's a very, 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 very delicate supply chains they have. All right, but now, okay, so here's a phase plot. It tells you got a little bit of a delay. That makes sense, right? So the supplier makes it a certain time. So if you just demand something and it's not in inventory, they'll say, well, the delivery period is a month or so many weeks because it still has to be made. All right, so it has to come through that supply chain. So you can see here, 180 degrees phase shift. Now that is the delays, and when you do a demand order, this is going to be the delay. You're going to find out. All right? Huh? Of course, if you're just force feeding somebody, there's no delay whatsoever. Right? Huh? Okay. Now, one of the interesting things, and this is why this research was done, during COVID, there was a big shock. So the customers all of a sudden, and we saw that before in the other call, they stopped buying things. So there's a huge shock on these things, okay? And in an impulse of a big shock like that, there's a lot of frequencies. And what they noticed is the, the supply lines went unstable, and they called that the bullwhip effect. And why? Because it kind of looked like a bullwhip, right? So it looked like this. Choo, choo. It's like a big whip that apparently is a whip that you whip bulls with. Huh? I don't know why this thing is all of a sudden. Is it stuck? Huh. Huh. It's a whip where you can whip bulls with, and apparently it makes this kind of shape. So if you look it up on the internet and the bullwhip effect, it's a really serious supply chain problem. And they won't know what to do with it. But here you can, with this type of filtering, you can see that what happens is you hit it at the resonance peak, okay? And if you do that, then this thing won't dampen out. It will actually amplify, and you'll get this, if you start shocking, this thing will go nuts, all right? So you want to be careful that when you design these supply chains, that you don't excite it with these frequencies. And if you do, that you have some kind of controller or some other better filter that has a lower resonance peak. I don't know. You guys learn these Butterworth filters and all this stuff. There's something you can design, so at least you get rid of these awful peaks. So you will know where you put them at frequencies where you don't have them. All right. So this is here's another graph where you can see that this intermediate really evens out the irregularities, right? Here they'll have to, if this is the production frequency, they really is awful, it's really not good for the customer. And if the customer's king, then this won't work. All right? Now, these supply chains have been of very high interest in the past during COVID, but now again with these tariffs that are being played with, So with tariffs, what the problem is that when a car is made, nobody knows where the car is exactly made, because some parts may be made in Japan, others in Mexico, others in the United States. We're talking now from the American perspective, we're placing the tariffs. And then the business of the cost of the tariffs is you have to look at what they call the transfer pricing. So, where these price differences get very big, that's where you assume if this is located in one country, then this part will have to be tariffs on. But if you put this in the same country, you won't. Okay, so the problem of tariffs, to do a correct analysis, is all about how the supply chains are structured and how you can optimize them. And for this, signal analysis is just a phenomenal tool, you know, filtering and then controls. And I just don't, you know, this is maybe where I want to end this lecture. Like, you can use these signal analysis tools so fruitfully in economics. There's a lot of insight, and it also is a formalization of the way these people think already. All right, so there's no if you say, oh, okay, you just go in the frequency domain, or this is the Laplace transform, nobody will know what you're talking about. But if you say this is the present value, you say, well, okay, that makes sense. You know? And I multiply by S. They won't know what you're talking about. You say, well, I'm imputing this income. Oh, no, okay, that makes sense, you know. So by going this way, not only do you guide your own intuition, but you're also capable of making models that other people can understand and use. All right. And simultaneously, you can see just how powerful these signal analysis tools are. I mean, there is no way, I believe, that if you start with a model like this, you'll get anywhere close to analyzing the Woolworth effects or something or equilibrium models, right? Yeah? So there's a great deal to be done for a good signal analyst. So for those interested to learn more, I have a couple of things on the internet. There are some whole series of lectures where I show how you can draw up these LTI models. There's a paper here on the foundations of that. There's a couple of other papers that are coming out on how to use this something we call economic circuit theory, how you can build these models, like that model of Behrendt. And there are a whole bunch of lectures and presentations that you find here. So with that, I'd like to end this lecture, and